Okay, in a few short minutes, we will start with by presenting Professor Griffiths, and he will give his talk. We are waiting a couple of minutes we're waiting a couple of minutes to let everyone back in, because we are ahead of schedule by like 5 minutes, and so we will just wait a little bit. On the meantime, maybe Paula. No, it's not a good idea. No, don't.
I can't share.
Don't do it. Don't do it. So we are now transmitting live in YouTube. And we are also recording these sessions to, well, several of us are recording to just in case there are some connectivity problems with any of us, then the others will have a copy of the file. And so we're just implementing safety nets, because we all know that these kind of things happen. So we still have people joining in the we have people joining the meeting, and we have a couple of minutes left to start the broadcast. Well, okay, no, the broadcast it started, but to start the talk right on time. So on the meantime, maybe I can tell you that, give me 5 seconds. Maybe I can give some announcements, public service announcements. Tomorrow we will have 4 talks. Starting at 10:30 Chilean time by Katie Tenenblatt first from Brasilia, then Ricardo Salvatimani from Rome. Then after lunch, after Chilean lunch, we will have Ernesto Lupercio from Mexico, and we'll finish tomorrow with Samuel Gruszewski from Stony Brook University in the United States. And on Friday, we will have 3 more talks by Alessandra Sarti from Poitiers in France, then Arnaud Beauville from the University of Nice in France. And we will finish the workshop on Friday right after lunch, after Chilean lunch, with Cecilia Salgado from Rio in Brazil. So we will, by the way, we will implement the following. So now we're on time. We will implement the following system for the questions. We will leave the questions to the end, and you can ask for, you can, don't ask the question in the chat, just ask for us for some time at the end. And so I will write down everyone that wants to ask a question in the chat. I will write it down, and we will just call everyone one by one at the end to ask the question to Professor Griffiths. Okay, and so you just write it in the chat, and I will take the notes. Okay, so now we're on time. Okay, it is a great pleasure to present Professor Dr. Phillip Griffiths, who hardly needs an introduction to geometers, because regardless of the geographic location of us or the area of research within geometry, we have all heard his name multiple times. He's an emeritus professor at the Institute for Advanced Studies in Princeton, New Jersey, which he directed between 1991 and 2003, and was elected a fellow of the American Mathematical Society in 2012. He currently is an essential member and part of the Institute of Mathematical Sciences for the Americas at the University of Miami. Among his most important honors stand out his plenary and invited conferences at the International Congress of Mathematicians in 1970 and 1978, respectively, and in 2008, the Wolf Prize and the Brouwer Medal. In addition, in 2014, he received the Leroy P. Steele Prize and the Chern Medal, both recognizing a lifetime of outstanding achievements in mathematics. His book, Principles of Algebraic Geometry, written together with his collaborator and a former student of his, Joe Harris, is one of the most important books in the area. And his main area of research is complex algebraic geometry. Let me repeat again that I will take, so just write in the chat if you want to ask questions at the end, and I will and we will open your microphone at the end so you can ask the question. Okay, Professor Griffiths, thank you very much for joining us.
Okay, thank you, Maurizio, for the introduction, and for you and your colleagues for the invitation to give this talk. I think this is supposed to be a talk that is for a general audience, and so parts of the talk will be rather elementary, rather classical. I'll try to put in a few things that are more current, our interest. On this overhead is the outline of the talk. To begin, I think modern Hodge theory is both a subject of study and of interest in its own right, and also it is a subject that is used in many areas of current mathematics, especially but not restricted to algebraic geometry. The main focus of this talk will be not on Hodge theory as a subject of itself, but on its uses. And I will give some of the historical evolution beginning really in the 19th century, and we'll discuss a few of the ways in which Hodge theory is used in modern mathematics. It relates to many different areas, to analysis, linear analysis, classical complex analysis, modern complex analysis with the D-bar operator, ordinary differential equations, and also nonlinear analysis. Some of the uses are listed there on the overhead. Relates to differential geometry. It provides a tool for using Hodge theory and algebraic geometry for proving vanishing theorems, general type and log general type properties of algebraic varieties, moduli, of moduli spaces, hyperbolicity, things like that. Relates to topology, both the topology of smooth varieties, that's where it began, but of general algebraic varieties, singular or non-compact, even relative homology or cohomology of algebraic varieties. Relates to intersection cohomology, and especially it relates to the topology in families of algebraic varieties where all of the above enter into the story. Finally, it relates to Lie theory, to homogeneous complex manifolds, and both compact and open. And these are usually called period domains, and they're compact duals. Classically, it's the upper half plane in the Riemann sphere. Relates to, and finally, of course, it relates to algebraic geometry. Today, we'll only have time to talk about a very few aspects. We'll not be able to talk about the central problem in the subject, the Hodge conjecture, mirror symmetry, which is an area of considerable current interest and research, other topics related to physics, character varieties, again, a topic of a lot of current activity, arithmetic, algebraic geometry, and so forth. Specifically, the use of Hodge theory to study moduli requires geometric constructions arising from Hodge theory, frequently some sort of what is called Torelli property, meaning that the Hodge structure on the cohomology in different ways determines the variety up to some finite data. So a Hodge structure and some of its generalizations are given by linear algebra data. And in some cases, from that linear algebra data, one may, using geometric arguments, make constructions which then can be related back to geometric properties of the algebraic variety you're interested in. This has very classical origins in the original use of Hodge theory, elliptic functions, and Riemann theta function that I'll recall in a moment. And it continues to find applications. Going to the origins of Hodge theory, I think there's no single work that one can say, here is the beginning. However, an important part of where it began was in the study of integrals of algebraic functions, like one studies in classical complex function theory. By an integral of an algebraic function, one means the expression written there, an algebraic function is a root of a polynomial in two variables, so it's not single valued. And so the integrand is, I'll explain in a minute how one has to interpret it, but these are the expressions with whose understanding was a large part of some of the origins of algebraic geometry. Such integrals arise in geometry, arc length, in mechanics. And for illustrative purposes today, I'm going to take just the simple polynomial y squared minus p of x, where p is a polynomial of degree 2g plus 2 with distinct roots. The integral on the previous overhead is understood to take place in the complex plane along a path avoiding the roots and along which we choose a branch of the polynomial. If the degree of the polynomial is 2, then as everyone learns in elementary calculus, you can evaluate these integrals by elementary functions. For example, the arc sine is one. The reason for degree 2 is that degree 2 equation is a conic, and conics can be parameterized by a line by stereographic projection as written here. If you change variables in the integral, then you get an integral of a single rational function, and you can use partial fractions to evaluate it in terms of rational functions and logarithms, elementary functions. However, as soon as the degree is 3 or more, the integral can no longer be understood in terms of what were called elementary functions. One of the first cases is the integral I've written here that turns up when you try to parameterize an ellipse by arc length. What sort of functions of arc length turn up when you write the x and y coordinates of an ellipse in the plane as functions of arc length? As far as the integrals go, I want to make both a topological and an analytic comment about them. I said that you choose a path in the plane. Here you're integrating between 2 points, and the value of the integral depends on the path. You can, of course, go between these 2 points by choosing a different path, as in the next figure. And just by Cauchy's theorem, well, I should mention here that the slit in the plane means that in the slit plane, you've chosen one of the 2 branches of the square root of p of x. If you cross the slit, you go from one value of the square root to the other. That's the rule. So if you then go from along this path or along this second path, then the integral changes just by Cauchy's theorem, and the integral along the middle path is the integral along the first path plus the integral around the slit. It's called a period. If you invert the integral by defining your x and y coordinates as functions of the value of the integral, then the indeterminacy, the choice of the path, is reflected by saying that the x and y values are periodic with periods, those integrals around those closed paths. So the simplest example is the arc length on the circle, and there you get the parameterization of the circle with 2 periodic functions, sine and cosine. Note also that the derivative of x is equal to y because the integrand is of the form dx over y. I think I've got that written here, yes. If you try to do the same thing with the elliptic integral, then because you have 4 roots, you get a different picture. You have 2 paths. I've written them here in the plane. One is the path that goes around one of the slits, that's delta. The other is a path that starts and crosses delta at a point, and when you cross the other slit, you go to the other value of the square root. So you have 2 closed curves with intersection number 1, they intersect at a point. If you invert the integral as in the previous overhead, then instead of singly periodic functions, you get doubly or multiply periodic functions. So the topological fact is the choice of the path of integration leads to periodicity of the functions obtained by inverting the integrals. For the analytic side of those integrals, when g is 0, if you have just 2 points, one slit, as here, Then near infinity, the differential that you're integrating, it looks like dt over square root of t. Integral blows up at both plus or minus infinity. On the other hand, for g equals 1, if you again set x equals 1 over t, just because you have a quartic polynomial, you get that the integral converges. So for any path, the integral along that path is finite. In fact, if you take the differential x to the power k dx over y remembers the square root of the polynomial p of x, those integrals are all finite. So when you have g bigger than or equal to 2, two things happen. You have multiple periodicity, and you have a bunch of integrals of algebraic functions that have everywhere finite integrals. Topologically, the picture is this. When you have just one slit, you open up the slit and make a picture like the thing on the left here. That's the one value of the square root. For the other value of the square root, you do the same thing and you join the two, as in the picture. You get the Riemann sphere. For g equals 1, you have a pair of slits, you make the same construction, and you get a torus. So what about the general integral of an algebraic function? For this, this is where Aldo's theorem comes in. You take an arbitrary polynomial depending rationally on a parameter t, for example, a family of lines in the plane, and you look at where your algebraic curve intersects the variable points given by the solution of the equations f equals 0 and h equals 0. Okay? That will have a number of points in common. The number of points is the product of the degree of f and h. That's Bezout's theorem. Usually you write these points of intersection in the form that's written here, the sum of the xi of t, yi of t, or just the sum of pi of t. And what Aldo recognized and proved is that even though those individual integrals of algebraic functions are very mysterious, they're quite complicated, highly transcendental objects, the derivative of the sum is a rational function. So that's the statement of Aldo's theorem. His proof, he gave several proofs. Some of the proofs you could teach in a first course in calculus. Quite ingenious calculation, but elementary. So what that means is that even though the individual integrals are complicated, their sum is an elementary function. Okay. If you invert the integral as done here, then as a consequence of this, one is going to be able to express the values of the x and y when you add periods in terms of the value of x and y without the periods. And really, for the ones we're interested in, all you need to do is to worry about x because its derivative is the y. Okay. If the rational function that appears in Aldo's theorem here has no poles, I said residues here, what it should be is poles, then the integral itself is a rational function. And what that allows you to do is to express the value of the x coordinate as when you add a period as a rational function of x and its derivatives at the other points. The last one here should be x prime of u. If you take a linear function as above, then what you get is this addition theorem that the value of x at u plus u tilde is a rational function of its values as written there. Okay. So for the degree 4 polynomial, when G is 1, this is the addition theorem for elliptic functions. And it's not the Weierstrass function when you use the quartic, it's related to it. Aldo actually defined the genus of an algebraic curve as the dimension of the space of those differentials, the differentials involving algebraic functions that were everywhere finite. Okay. This was his definition of the genus of an algebraic curve. It was just those expressions such that no matter what path you integrate along, you always get a finite answer. You get no singularities. Riemann proved that that genus is 1/2 the first Betti number of the corresponding topological surface, and that the first cohomology is the direct sum of what are called the holomorphic differentials, the H0 of omega 1, that's the notation in algebraic geometry, direct sum the conjugates of those differentials. That's a 2G dimensional vector space. The argument for the second part used the cup product in cohomology. Riemann called it first and second, the bilinear relations. First, just trivially, omega wedge omega is 0, omega wedge omega conjugate times I is positive, and that led to this direct sum decomposition. That's the Hodge structure on the first cohomology of a compact Riemann surface that you get by taking the desingularization of the algebraic curve f of xy equals 0, assuming it's an irreducible polynomial. That was the beginning of Hodge theory. That's related Hodge theory, meaning initially the study of the integrals of algebraic functions. It related that to topology. Finally, on the historical side, just a few words about Picard. The reference here is the 2 books on algebraic surfaces by Picard and Simard. He studied algebraic surfaces. Those were very concrete objects. They were surfaces in 3-dimensional projective space. He studied them by looking at the pencil of algebraic curves. You simply hold z equals constant and think of having an algebraic curve depending on the parameter z. Okay. Picard proved that first, they're curves lying on the surface obtained by intersecting the surface in 3 space with a plane. Those are connected. The 0th homology map is an isomorphism. And the first homology of the curve maps onto the first homology of the surface. So all of the first homology lives on the algebraic curve given by intersecting the surface with a plane. He also considered differentials, this time of 1 forms with finite integrals, and of 2 forms. That's the new object that appears when you go to surfaces. For the first of these, he showed that any differential that had everywhere a finite integral was closed. And from that, Picard was able to show that the first homology of the algebraic surface, that should be x here, not y, had a Hodge structure of weight 1. Okay. That it was isomorphic to the vector space of differentials that satisfy this, plus their conjugates. In modern terms, his argument was just the one written there. If it's not closed, then you get a contradiction from Stokes' theorem. Picard also defined the Picard number Picard number was the number of linearly independent homology classes in the second homology, which were represented by algebraic curves lying on the surface. Okay. And what he showed was the second cohomology has these two summands, the differentials of degree 2 that have everywhere finite integrals, their conjugates, and a certain number of, the certain number of copies of the complex numbers were given by this Picard number. For the third term here, the next part of the story was the Lefschetz 1-1 theorem, which identified the integral homology in degree 2 with the orthogonal to the part given by the everywhere regular differentials of degree 2 as the Néron-Savary group. Okay. So we identified what this piece was. The full story to make this contained into an equality so that this Picard number part was actually a subspace of something that was identified, that awaited the work of Hodge. It's now H11 in the notation of Hodge theory. So that was the story of Hodge theory in very summary form up until the time of Lefschetz. Now I'm going to just review briefly the objects of Hodge theory. These are linear algebra objects. First is a polarized Hodge structure given by a vector space with a bilinear form and a filtration on the complexification satisfying this condition to be opposite. The usual picture one has of a Hodge structure is a direct sum decomposition into conjugate subspaces, and those are equivalent. This defines the summands, and this defines the filtration if you have the Hodge decomposition. So this is a Hodge structure of weight n. The polarization arises from the first and second Hodge-Riemann bilinear relations that we won't use here. I mentioned special cases of them before. The basic example of a Hodge structure, of course, is the cohomology of a smooth algebraic variety. It has a Hodge structure of weight n. The polarization comes, the bilinear form comes when you have an ample line bundle on the variety. So we think of it as being in projective space. Okay. A mixed Hodge structure, that's a rational vector space with two filtrations, a weight filtration increasing, a Hodge filtration decreasing, and the Hodge filtration induces a weight K Hodge structure on the associated graded, the successive quotients. So although it does not have a Hodge decomposition, there is a canonical decomposition, Deligne decomposition. That should be M there, the weight, the length of the weight filtration into so-called PQ parts. And instead of a direct sum with the conjugacy condition that we had for a Hodge structure, you only get the conjugacy condition modulo stuff of weight 2 less than where you are. So the weight filtration and the Hodge filtration are given by the same formulas as in the ordinary Hodge structure case. You just only have this condition here. One word about extension data. In practice, one always has not just a rational vector space, but a lattice. Think of integral homology and cohomology, and that induces lattices on the successive gradeds. So a mixed Hodge structure is a successive extension of Hodge structures. The first level are just X'd ones, And I've written out what it is here. And this, if you work it out, is actually a compact complex torus. So the first level extension data are compact direct sums, so compact complex tori. In general, the set of at most k-fold iterated extensions of with fixed associated graded give you a sequence of fibrations, and the fibers are again direct sums of x1s. Only here the separation is by k. That's the level of the filtration of the extension. So the standard example, as I mentioned, of mixed Hodge structures is the cohomology of an arbitrary algebraic variety or a pair consisting of a variety and a subvariety. A variation of Hodge structure is a family of Hodge structures. So it's a local system with a filtration on the corresponding complex vector bundle, connection, a flat connection that defines the local system or the sections of the local system, the so-called Gauss-Menin connection, and there's a differential constraint. There's also a horizontal bilinear form that polarizes a Hodge structure on each fiber. I didn't write that down. Here, the standard example is a smooth family of projective varieties. You look at the cohomology along the fiber. The Hodge bundles give the Hodge structure on the cohomology along the fibers, and the Gauss-Menin connection, that tells you geometrically what cohomology classes along the fibers are obtained just by transporting a fixed cohomology class to the nearby fibers because they are topologically the same. An infinitesimal variation of Hodge structure is given by linear algebra data, graded vector space with a map such as here, with satisfying this condition, that if you iterate the map twice, you get 0. So it's module over the symmetric algebra on T. And the standard example is the associated graded that arises from a variation of Hodge structure, and the T are the tangent spaces to the parameter space, and theta is the map induced by the Gauss-Menin connection. Finally, a limiting mixed Hodge structure, it's a special type of mixed Hodge structure where the weight filtration arises from a nilpotent endomorphism. A nilpotent endomorphism on a vector space gives a unique filtration satisfying these two conditions. Drops the weight by 2 and the hard Lefschetz type of condition. I'll say more about this later. I forgot a third condition here, that N should drop the Hodge filtration by 1. FP should go to FP minus 1. I just forgot to put that in the overhead. There are also bilinear forms in the data, which we won't be concerned with here. The standard example is if you have a family of smooth algebraic varieties over a punctured disk, then the monodromy, what you get by taking a homology class and going around the origin in the counterclockwise direction, is a quasi-unipotent transformation. That is, the semi-simple part is of finite order. The eigenvalues are roots of unity. And moreover, the unipotent part, so it's the exponential of a nilpotent matrix, and the index of unipotency is no bigger than the degree of the cohomology you're interested in. Okay. The basic result due to Schmidt is that if you have a family of varieties over the disk with a singular one over the origin, then the corresponding Hodge structures have a limit as you go into the origin, which is a limiting mixed Hodge structure. Okay. So actually, all you need is the family of Hodge structures over the punctured disk to get a unique limit at the origin. If you think of moduli, if you have a family of smooth varieties over the punctured disk, it's a major issue to uniquely fill in the origin. Hodge, theoretically, there's a unique way to do it. And that's one reason that Hodge theory is useful in moduli questions, because the unique way of filling in the origin, Hodge theoretically gives you a clue as to what you should try to fill in algebrogeometrically. This was extended to several variables by Catani, Kaplan, Schmidt, and I've just discussed really the basic example. I think I won't get into this here just for time. So some of the geometric applications of Hodge theory. In some situations, one may associate to a polarized Hodge structure or an infinitesimal variation of Hodge structure, a geometric object. The classic example associated to a weight 1 polarized Hodge structure is a compact complex torus and a line bundle. The line bundle has Chern class given by the polarizing form, the skew symmetric form that gives the polarization. From the Hodge-Riemann bilinear relations, this line bundle is, well, it's a holomorphic line bundle. It's positive and therefore ample. If, moreover, the alternating form is unimodular, like the first cohomology of a compact Riemann surface, then up to scaling, there's a unique section of this line bundle. That unique section then will give a divisor in the compact complex torus. Okay. This is the situation when you have the first cohomology of a smooth algebraic curve, and this then goes back to Abel. You map the algebraic curve to this compact torus just by integrating the holomorphic differentials from a base point to an upper limit. That gives a holomorphic map of the Riemann surface to this compact complex torus. Using abelian sums, as was done by Abel, the symmetric powers of X, that is the sums of D points, will map by abelian sums to points in the Jacobian. That's this compact complex torus. Riemann proved that if you take G minus 1 points, then you get a divisor. You map those in by the abelian sums. That is the theta divisor. So what is happening is from the Hodge structure, you construct the right-hand side. It's a geometric object. It's a divisor in a compact complex torus. And that is equal to the G-fold symmetric product of the compact Riemann surface. So when G is 2, it is the compact Riemann surface itself. You've reconstructed it from its Hodge structure. The general Torelli theorem says that you can do this in general. From the theta divisor, you can reconstruct the compact Riemann surface. So the polarized Hodge structure determines the algebraic curve, the smooth algebraic curve. In general, it's not possible to do this in higher dimensions. The reason is the differential constraint that's imposed on the Hodge structures when the variety varies with parameters. Only in the classical case, when the set of Hodge structures is a Hermitian symmetric, is something like this construction possible. So what one looks for in higher weights, higher dimensional cohomology, algebraic surfaces, threefolds, and so on, is some surrogate for the theta divisor. One such surrogate is this infinitesimal variation of Hodge structure, the Hodge structure together with its first order variation. And a recent example of how this may be used, this was in the archive a couple of weeks ago, is the theorem of Shepard-Barron. If you have an elliptic surface with no multiples fibers and this condition on the Hodge numbers, the H20 is the dimension of the space of everywhere holomorphic 2 forms, H10 are the 1 forms, then the polarized Hodge structure on the second cohomology generically determines the elliptic surface. Okay. I mention this, A, because it's quite recent, and B, it's a very beautiful argument where you use both Hodge theory and geometry. The argument is centered around the ramification points of the J function mapping the base space of the elliptic surface to the moduli space of genus 1 curves. A classical example of using infinitesimal variation of Hodge structure is the theorem of the Nagy-Green. And that tells you that you can reconstruct generically a smooth hypersurface and projective space from its Hodge structure together with the first order variation of it. Okay. And there are a number of extensions of this. I'll mention some later in the talk. A more classical example, which was related to actually the Shepard-Barron paper I mentioned, is of using the infinitesimal variation of Hodge structure, turns out to be the following. If you look at an algebraic curve of genus 2 or more, then the symmetric power of the holomorphic differentials maps onto the global sections of twice the canonical, the quadratic differentials. Okay. For genus at least 3 and X non-hyperelliptic, this mapping is onto and proved by Max Noether, and again proved by Max Noether that for genus at least 5, the intersection of the quadrics through the canonical curve is just, that's the kernel of this map, is just the curve itself. Okay. So that gives you a generic global Torelli theorem for curves that's in genus bigger than or equal to 5. It's not as good as the Torelli theorem, but it's a type of argument that will generalize. I should mention here that this map is the infinitesimal variation of Hodge structure dualized for the moduli of algebraic curves, compact Riemann surfaces. So this is an infinitesimal variation of Hodge structure object here. And from it, you reconstruct the algebraic curve itself generically. I think I'm not going to have time to get into this another example that's more recent. I want to spend the last few minutes talking about a geometric example that is in fact related to what I was going to say earlier. This is dealing with moduli spaces of surfaces of general type and how one might use Hodge theory to get some understanding of what should go on the boundary, what surfaces appear on the boundary of moduli. So the existence of a moduli space of surfaces of general type proved by Kolar, Shepard-Barron, and Alexiev some time ago, they proved that that moduli space exists For algebraic curves, it's just m sub g, the Deligne-Mumford, the m sub g bar is the Deligne-Mumford completion. Kolar, Shepard, Baron, Alexiev proved that there's a canonical projective compactification of this moduli space. So the moduli space exists and it has a canonical compactification. Question is, what goes on the boundary? One knows the nature of the singularities. It's like for curves, you have just nodes on the curves that appear on the boundary. Here, there are so-called semi-log canonical singularities. And for algebraic surfaces, there's a list. It's actually a fairly short list of what those singularities can be. A part of the boundary corresponds to surfaces that are singular and have Gorenstein singularities. They're simple, therefore they're simple elliptic singularities or cusps. So I'll concentrate on the simple elliptic ones, okay? In contrast to the case of curves, where the completed moduli space is basically smooth, this part of the boundary of surface of the Kolar, Shepard, Baron, Alexiev moduli space is generally highly singular. And it's consideration of the singular data in the limiting mixed Hodge structures that suggest how one might go about desingularizing this part of the boundary. There's some notes where this is explained. I'll just briefly mention a few of the aspects of that here. So I will mention that this is one of the first non-classical examples I'm aware of where you actually construct a geometric object from a Hodge theoretic one, not its first variation, but just a Hodge theoretic one itself. In this case, the limiting mixed Hodge structure. That's a linear algebra object. And from that, one constructs this extension data, as I mentioned earlier. In the extension data at level 1, you have a compact complex torus, and one can use that to get at what should go on the boundary of the KSBA, what should be used on the boundary to help desingularize the boundary of a KSBA moduli space. So to continue that example, suppose that we do have a KSBA moduli space for general, so I'm going to give heuristic reasoning here, for general type surfaces that have this canonical completion. Assume that the moduli space is smooth and that a general point of M corresponds to a smooth regular surface. One may ask, can Hodge theory suggest what surfaces appear on the boundary? And can Hodge theory suggest how one might construct a desingularization? So here, the way one proceeds is as follows. One knows what the boundary components are Hodge theoretically. I mentioned earlier that there's unique limiting mixed Hodge structures. Limiting mixed Hodge structures have been classified. It's a Lie theoretic question. The principal boundary component consists of limiting mixed Hodge structures where the logarithm of monodromy as n squared equals 0 and the rank of n is 2. Okay? So one knows Lie theoretically what goes on the Hodge theoretic boundary. You want to work backward and say what then should go on the algebrogeometric boundary. The limiting mixed Hodge structure has for its associated graded Hodge structures of weight 1, weight 2, and a Tate twist of the one of weight 1. Okay. The H1 is since the rank of n is 2, is the first cohomology of a smooth elliptic curve. So given a KSB degeneration which has smooth fibers for T non-zero, what is suggested is that the singular one should have an elliptic singularity, a simple elliptic singularity, where the resolution of that singularity is a smooth surface in which this curve appears as the curve, as the desingularization of the elliptic singularity. Okay. The c squared, since it contracts to a point, c squared is negative, and from the semi-simple part, one can read off what c squared should be. It's the so-called Coxeter element in the monodromy of the corresponding simple elliptic singularity. So one knows c and one knows what c squared should be. Okay. So that gives you a clue what sort of elliptic surfaces should appear on the boundary. That's from the associated graded of the limiting mixed Hodge structure. Suppose you want to desingularize it. To desingularize it, you want to do semi-stable reduction. You want to know what you fill in over the origin to have a normal to crossing surface divisor on x tilde. Since n squared is 0, Hodge theory, the Clement-Schmidt sequence, suggests that the central fiber should have a double curve and no triple points. Should be two smooth surfaces meeting transversely along this curve C. That's a Hodge theoretically suggested answer. Okay. The simplest possibility then is you take the desingularization of the surface with the simple elliptic singularity and you glue it to some other smooth surface along the curve C. Okay, what should this other surface be? Should contain the curve C. That's an elliptic curve. Well, when one has an elliptic curve, one thinks of smooth elliptic curve, one thinks of smooth cubics in P2. Okay. On the other hand, for this object to be smoothable, it's a singular surface, it may not be the central fiber in a smooth family. There's a condition due to Bob Friedman on the normal bundle of C and X tilde with the dual of the normal bundle of C and Y. From the degree of the elliptic singularity, you know that degree D, well, that degree is D, and what you know from the previous one here is that you should blow up no more than 9 points. That's the max, that's the degree of a cubic curve in P2. So you should blow up no more than 9 points. And in fact, you know what, then that bounds what the degree of the simple elliptic singularity can be. It has to be between 1 and 9, and the surface is a del pezzo. Okay. Moreover, from this desingularized surface, you can construct the, from the limiting mixed Hodge structure, you can construct the X1 here. That's a that's a Hodge theoretic object, and it contains a factor constructed from the subspace of Hodge cycles in the H1 of the Y. Okay. So what this is telling you is from the extension data, from the limiting mixed Hodge structure, you have this Hodge structure of weight 1 and Hodge structure of weight 2. Hodge structure of weight 1 is the Hodge structure of an elliptic curve. And from the level 2 extension data, you're going to get a point in the Jacobian of the curve. Those are the points that you blow up. So the conclusion is that from the limiting mixed Hodge structure, you have a candidate for what you should put in to resolve the singularity in the KSBA moduli space when you acquire a simple elliptic singularity. You know which elliptic curve you should use. That's a Hodge theoretic thing. You know a bound on the degree of that singularity. And you also know which points you should blow up on the curve in T2 to construct the fiber that you fill in for the semi-stable reduction over the origin. It's this construction that then leads to the desingularization of an open set in this boundary component.
Okay.
And I had wanted to give some further applications of uses of Hodge theory. Some of the standard ones are in topology, dealing when I go back to Lefschetz. And some are in vanishing theorems, vanishing of cohomology. I think because of time, I won't go into those. They're in the notes. And I will just mention that in the appendix to those notes, the principle that one should, in a talk, have a proof of some fairly recent interesting result. I've given the argument for the local Torelli property. That is, the Hodge structure determines locally the surface in moduli for the first interesting surface that's not a K3 that one comes across of general type. K squared is 1, it's regular, and the PG is 2. It has 2 holomorphic differentials. The moduli space has dimension 28. The period domain has dimension 56. The infinitesimal period relation, the differential constraint, is a contact transformation. And what one finds is that the moduli space for these surfaces are a contact submanifold, maximal integral manifold of this distribution, really. It's a contact distribution. And that you have a local Torelli property so that at least up to finite data, the Hodge structure determines the surface. I think I will stop here and see if there are any questions. Thank you.
Thank you very much, Professor Griffiths. Maybe we can invite the audience to open their microphones and clap. Okay, to thank you virtually. So thank you again. And I didn't receive any question on the chat. Maybe let's see if anyone wants to, because I do have one very innocent question. Okay, so let me ask my innocent question first. We saw a cornucopia of different names of famous mathematicians, but I don't think we saw the name of Hodge. Right.
Here is Hodge. That if we go to topology,
so I'm a differential geometer, so I know what I know about Hodge theory is the finiteness of the Betti numbers using these analytic arguments, right?
Of course, Hodge proved the existence of a Hodge structure on the cohomology of a compact Kähler manifold, in particular of a smooth projective algebraic variety. So that's the basic theorem of Hodge as far as the existence of a Hodge structure on cohomology goes. What motivated Hodge, one of the principal motivations was to prove the following. So going back to Lefschetz, he showed that if you have a smooth variety, take a general hyperplane section, then the cohomology is the same up to 2 below the middle dimension. That's the theorem of Picard for surfaces that a general plane section of a surface is connected, and that this map is injective for Q equals n minus 1. That's the theorem of Picard that the H1 of the curve maps onto the H1 of the surface. Okay. So this was proved by Picard when n is 2, and Lefschetz's argument was it's really an extension of Picard's argument. The other results of Lefschetz, this is a purely topological result, by the way, that if you have a topological situation that looks like the one that arises in algebraic geometry, you don't use the complex structure, you just use the topological picture, then you get this theorem. It's a topological result, essentially. The other result of Lefschetz concerned the mapping given by the cup product on cohomology of the dual to a hyperplane class. And Lefschetz proved that this is an isomorphism. It's called the hard Lefschetz theorem. The reason it's said to be hard is that this result is deeper than the earlier one. Lefschetz's original topological argument for this was incomplete. And it was trying to prove this theorem that was motivating, or was a large part of the motivations of Hodge's work. He wanted to give a proof using analysis of this theorem, or using Hodge theory, what turned out to be Hodge theory. So not only did Hodge prove the existence of a Hodge structure on cohomology, but this on the cohomology ring of a smooth algebraic variety, he proved the hard Lefschetz theorem, which is, I think it is the deep result. I mean, it leads to everything almost. And that was really a tour de force, Hodge's argument for that. It is interesting that Picard gave a statement of this theorem for surfaces, and I think he gave what he said. He gave a proof. It's in Picard and Simard, and I think that proof is probably correct, because he had the Hodge theory for the hyperplane section, the algebraic curves, and the Poincare complete reducibility theorem for abelian varieties was known. And that's a Hodge theoretic result. And using that, I think Picard's proof of the hard Lefschetz theorem is probably okay. But that breaks down completely when you get above algebraic surfaces. That really is where Hodge theory in its full glory had to be used.
Okay, thank you. Thank you very much. Any other question? Maybe we just keep the microphone open for anyone that wants to add anything. No? Okay, very good. Well, we thank Professor Griffiths again. Thank you very much. It was a very interesting talk.
Well, sorry that it got, there was more than I had time for. I knew that would probably be the case. So there are these notes that I think you'll probably post, that also there's a fair number of references that I gave, mostly to some of the classical work, but also some of the more recent things, like, for example, the Shepard-Barron result.
Yeah, so I think, well, we have a copy of your presentation, and we can easily post it to our web page, and with your permission, of course.
Sure, that's fine.
Yes, and I also saw that there are some links to some of your lecture notes that you have given in talks in Miami right now, right?
Yes, and so there are proofs of some of the things that are just sketched
correct
or even alluded to here. For example, some of the classical relations of using Hodge theory to prove vanishing theorems in cohomology. That's a very interesting story, one that continues to be useful, and there's some links to that type of result also.
Excellent. So thank you again, Professor Griffiths. Please open the microphones again to clap once more to finish our first day of the conference. And so everyone is invited tomorrow. We will be sending links to everyone that when registering asked to be part of the second day of the workshop. And so we will meet tomorrow, 10:30 Chilean time. You do the numbers, please, because everyone is in different time zones. Thank you again to all the participants. It's very nice to see many of our friends here that have been here in Chile. I see Milagros, I see Alessandra. Well, Professor Griffiths also visited us a few years ago. Well, by names, I see many of our very, very dear friends from Chile and abroad. And thank you again. And we will close the session now and see you tomorrow. Okay, you're very welcome, and thank you for being with us.